The goal in this video is to connect convergent sequences to the notion of open sets, and more specifically, open balls. Open balls. And we're going to do that by proving the following claim. So, claim, if P is a limit point of the set S, then there exists a convergent sequence of points. There exists, or I'll just say for now, there exists a sequence of points, all in S, that converge to P. Notice that the machinery that we use to connect convergent sequences to open sets is precisely the idea of the limit point. So let's remind ourselves of what the definition of a limit point is. So remember, if P is the limit point of a set S, then this implies that every open ball with center P, every open ball with center P, so every open ball centered at P, contains a point, I'll say Q in S. So P is the limit point of a set S, so every open ball with center P contains a point Q in S, where Q is not equal to P. So check this out. Let's go to our picture here that I've drawn. I can take open balls of arbitrarily small radii, and in each of those open balls, no matter how small I choose the radius of that open ball to be, I'll always be able to find a point Q in S such that Q is not equal to P, where Q is in that open ball. So check this out. If I have the rate of an open ball like this, and this set in orange, this outline in orange, this is my set S here. This is my set S. So I'll always have area in this open ball that's this S. We can think of all of the black space that's within this orange outline as S, as points in S. So every open ball, no matter how small I take my open ball to be, I'll always be able to find, and this open ball, I should say, has center point P. So the centers of all these open balls, I know I haven't drawn it very well, but the centers of all these open balls are in fact this point in blue, P, which we'll call P. This point in blue we can think of as a limit point of the set S. And remember, I've talked about in previous videos how you don't want to be limited by a picture, but oftentimes it can propel you forward in a proof. But don't limit yourself, and don't let it be a box that you put yourself in and inhibit you from coming up with creative ideas for solving a problem. But this is a nice way to kind of propel us forward and have an idea and give ourselves an idea for proving this claim in yellow here. Because I can, again, just to reiterate the fact, I can take an open ball of arbitrarily small radius that's centered at P, and I'll always have area in this open ball, or that is to say, I'll always have points in S that are in this open ball that are not equal to P. So check this out. This is gonna motivate how we're gonna prove this statement, how we're gonna prove this claim. So check this out. Let me write proof. So consider the open ball of radius 1 centered at P. And just a quick aside here about notation. I'm gonna talk about open balls and where I'm gonna talk about the subscript is the center of that open ball, and the superscript is the radius of that open ball. That's the notation I'm gonna use. So consider the open ball of radius 1 centered at P. So we're gonna call that B sub P with radius 1. So consider this open ball. Then there exists a Q1 in S. Let me erase this BP real quick. There exists a Q1 in S, and a Q1, this Q1 is also in the open ball centered at P with radius 1. And then also, thirdly, this Q1 is not equal to P. So check this out. Check out what I can do. There also exists an open ball with radius 1/2 and center P. So I'll call that B sub P with radius 1/2, such that this open ball contains a Q2 in S. And this Q2 is also not equal to P. So check out what I can do. I can do the same thing. I can keep this this idea going forward with arbitrarily small radius. So check this out. There exists a Q3 in the open ball centered at P with radius 1/3, such that Q3 is not equal to P. And I'm going to do one more just for emphasis. There exists a Q4, and this, I forgot to say this Q3 is in S. So there exists a Q4 because, again, P is the limit point of this set S. And by definition, this statement must hold. So there exists a Q4 in the open ball centered at P with radius 1/4, such that Q4 is not equal to P, and Q4 is in S. So check this out. Continuing this for any radius 1/n, there exists a Qn in the open ball centered at P with radius 1/n, such that Q sub n is not equal to P and Q sub n is in S. So check this out, and let me point out an interesting fact here. These like Q4 and Q3, for instance, are not necessarily distinct. They don't necessarily have to be different from each other. But it's an important point to notice that fact that these 2 points in this the sequence Q3 and Q4 are not necessarily distinct. For instance, I could have the sequence 1, 1, 1, 1, and so on. An infinite sequence of repeating ones. And this sequence is in fact a sequence, and I could relabel this sequence as A1, A2, A3, and so on. It just so happens that each AI is equal to each other. And that is to say, each term in the sequence is equal, even though they're labeled differently with different indices. So check out what we've done. We've created a sequence of open balls that get progressively smaller. So that is to say that this sequence of open balls, I can always find an open ball in this sequence that has a radius smaller than any number. And any point in that open ball is a distance away from P strictly less than that arbitrarily small radius. So that leads me to the following claim. Check this out. I claim the sequence Q1, Q2, Q3, and so on that we've created in here, that sequence of Q1, Q2, Q3, and so on converges to P. And so to prove this, I'll remind you of the following fact. Check this out. We know that there exist arbitrarily small rational numbers. Said differently, in a way that's very helpful for proving the convergence of this sequence to P, that for any epsilon strictly greater than 0, there exists a capital N in the positive integers such that 1/n is strictly less than epsilon. And check out what I also know. I know if n is strictly greater than, not 0, n is strictly greater than capital N, which is, of course, in the positive integer, so therefore it's strictly greater than 0, then this implies that 1 over n is strictly less than 1 over capital N, which is, of course, strictly less than epsilon. So check this out. Check out what I can do. I know that if Qn is in the open ball centered at P with radius 1 over n, then this implies, by definition of an open ball, remember, an open ball, each point in an open ball of center P, each point in an open ball of center P must have distance away from P strictly less than the radius. Let me say that again. Each point in an open ball of center P must have distance away from that center P strictly less than the radius by definition of an open ball. So therefore, if Qn is in the open ball centered at P with radius 1 over n, then this implies that the distance between P and Qn is strictly less than 1 over n. But check this out. Check out, based off of this, this is strictly less than epsilon whenever n is strictly greater than n, which is exactly proving by definition of convergence that this sequence Q1, Q2, Q3 converges to P. We have just shown that given any epsilon strictly greater than 0, there exists an n, a capital N in the positive integers, such that the distance between P and Qn is strictly less than epsilon whenever n is strictly greater than n. That is to say, whenever I have a term in this sequence that comes after capital N, the capital nth term, then that distance between P and that lowercase nth term must be strictly less than epsilon. So therefore, we've just proven that this sequence here, this sequence converges. And therefore we've proven our claim that if P is a limit point of the set S, then there exists a sequence of points all in S that converge to P. And this was our way of connecting the notion of convergent sequences to open sets, which comes into play when we talk about a statement in the language of convergent sequences, and we want to translate it into a possibly simpler statement in the language of open sets.